Hi everybody, we're going to move on to a different subtopic now. We're still in the topic of periodic motion, which circular motion was part of, because obviously in circular motion there's a repeating periodic element to that motion. But we're going to look at a different one now, which is called simple harmonic motion. And you can probably tell from the two highly technical animations that you can see there that this is to do with essentially a form of oscillation, something moving, in the case of the mass and the spring, on the left up and down, or with the pendulum left to right through an arc. Actually, technically the pendulum is following a partial circular motion path, but it's non-uniform, which we will look at in a little bit. What I want you to do though before we start is consider both these systems and the similarities between them, and try and describe the motion of both systems in as much detail as you can. Okay, so have a look at them, pause the clip for a second, have a look at them and just write down as much detail you can about the motion of these two systems. Hopefully you've had a go at that. The reason that I ask you to do that is because one of the key aspects about dealing with simple harmonic motion is being able to accurately describe what's going on at the different points in the cycle. So I'm going to show you now what I would put if I was simply asked to describe an object in simple harmonic motion, as these are, and see how close you've got to some of these points. Now there's a couple of absolute key points that I won't cover here because that'll be a bit of a spoiler for what comes later on. Okay, so the first thing to consider is actually before these objects, and this applies to both objects, these points will apply to both, before these objects are set into motion, they would initially just be sat at rest. The spring mass system would have found an equilibrium position and wouldn't be oscillating, and the pendulum would be hanging vertically downwards. So if nothing's done to the systems, they don't go into motion at all. There are forces already acting on them. So in the case of the spring mass system, there'd be some tension in the spring and the weight of the mass, but they would be in equilibrium with each other, so it would be stationary. In the case of the pendulum, again, there's a tension there and the weight and exactly the same. They're in equilibrium, so there's no acceleration and it's at rest, so therefore no motion. So to get it into motion, what that means is an external force must be applied. Now, when dealing with these systems, you can consider all the forces acting on them. It does make the maths much more tricky. Because these forces are already acting in a stationary position, what we really look to do is just look at how changes in forces, so changes in the tension, for example, because obviously the weights won't change, how the changes affect the motion and create a resultant force. So it's easy, for example, in the spring mass system just to ignore the weight because that's constant all the way through. So there's always a component of tension that's countering the weight, but it's the change in tension from that contributes to the motion. So to get simple harmonic motion in effect, we have to displace the mass, and in both cases it is the mass, from its equilibrium position. And to do that, you need an external force. Okay, it's not just going to happen by itself. We're going to have to put a force in place. Okay, now just before this point, really thinking about it, when it's held in that displaced position, if you hold it there, then it will reach a new equilibrium. Okay, the forces, internal force in the system will have to change so that they balance the external force that's applied. And then the key thing is when you remove the external force, that means we've got additional force within the internal forces in the system that then act to return it to its equilibrium position. These objects want to be in equilibrium, so that's where they try and get to. And because we've got a resultant force acting simply by Newton's second law, that means we get an acceleration. The object accelerates back towards its equilibrium position. When it gets there, the forces are the same as they were when it was completely at rest. So they're back in equilibrium, back in balance. So the resultant force is zero and there's no acceleration at that point. Okay, so we can easily see, just with a little bit of common sense then, that we had a maximum force and therefore a maximum acceleration when we were in our maximum displacement, the furthest point away from equilibrium, and that it's therefore got to reduce the size of the resultant force will reduce as the object reaches equilibrium until it reaches zero at that point. And at the equilibrium position, okay, this object's been accelerating towards it, so it's not going to behave like it did when it was totally at rest. It's now got momentum. It's been accelerating, so it's got velocity and therefore momentum. So it's going to have some inertia that just carries it straight through that equilibrium point. So this is why it doesn't stop when it gets back to equilibrium. It's got that inertia to carry it on through. You can also consider this actually in terms of energy stores and transfers as well. Obviously, we're starting by increasing the potential energy of the system by displacing it from its equilibrium. We're increasing the potential energy, then we release it, it converts it to kinetic energy, and therefore it has some velocity as it goes through the equilibrium position. We will look at that in a few weeks' time in a bit more detail. Okay, once it's gone through that equilibrium position, then the restoring force then starts to increase again and is now acting in the opposite direction, trying to get it back to its equilibrium. So it's whistled past the point where it'd like to stop, and the restoring force then starts to increase to get it back to where it was originally. Restoring force is a term that essentially means restore it to equilibrium. In this case, it's equal to the resultant force acting. So the object will first need to be decelerated. It's got to slow down, and then it will then accelerate but change direction to get back to equilibrium. So it'll be heading off one direction past equilibrium, it'll slow down, reach a stop at some point, and then come back. But what it means is that restoring force is always acting in the opposite direction to the displacement. Providing that we meet certain parameters, chiefly that there are no other external forces acting, namely friction or any resistive forces like that, the cycle will repeat indefinitely, providing no energy is exchanged to the surroundings, so no energy is lost, and we're not putting any external forces on to add energy into the system either. Which means that we've got a system that is said to be oscillating, because it repeats what it's doing continually in a cyclic fashion. So that's quite a lot of depth just to describe a pendulum going backwards and forwards. I would imagine some of you wrote it goes backwards and forwards or it goes up and down. And you can see the sort of level of detail that's actually needed. And some of the keywords we've got to be talking about: forces, acceleration, velocity, displacement at the very minimum, if not including momentum in there and energy changes as well. So, but just some of the key features of the system. Okay, that we can sort of ascertain just with a bit of common sense from there. At the amplitude, okay, so it is maximum displacement, what we've got, excuse me, is that the acceleration is also at its greatest. If it's got maximum displacement, it's going to have the largest resultant force and therefore the largest acceleration, trying to return it to equilibrium. And we also know that the velocity is zero. So at the amplitude of the oscillation, the velocity is zero. Okay, that's because at that point it's changing direction. At the equilibrium position, we kind of get the reverse scenario there. At that point, we've got zero resultant force, and so no restoring force, zero acceleration, but we've got maximum velocity. It's been accelerating all the way to that point, so it's going to be at its maximum at that point. Again, you can consider that both in terms of forces or in conservation of energy. Both work really well on that one. As a general point, that means the acceleration is always in the opposite direction to the displacement. If you move it to the right, it accelerates to the left to get back to where it started, and vice versa. And if it's up, it will accelerate down, so on and so forth. And the initial displacement is equal to the amplitude of the system. Okay, you will never ever get a displacement that is greater than how far you initially moved it. Again, providing you don't put then further energy into the system. If you just leave it alone, it will max out at that particular displacement that you started at. That is just really simple conservation of energy rules with that. The amplitude may decrease each cycle if there are resistive forces, which we mentioned we would neglect in certain circumstances. Again, in future lessons, we will look at what happens when the oscillations aren't free. Okay, it's worth mentioning here, it's not on the slide, but a free oscillation is when it is just moving with absolutely no external forces at all. So it's moving it to what's called its natural frequency. We'll come back to those points again in later lessons. So let's look specifically at we've done generally everything we've done so far covered both systems. Let's look a little bit more specifically at the first one, the spring mass system, which is actually the easier one of the two to analyse. Okay, now the original displacement of the mass from equilibrium is due to an external deforming force, and we can actually use Hooke's law here to describe what happens to a spring when you extend it. So that deforming force is equal to the stiffness of the spring multiplied by its extension. And in this scenario, the extension is the same. The extension of the spring is the same as the displacement of the mass, and the deforming force is the additional force you've applied. So we're not including any forces here when the spring was loaded with the mass originally. We're not looking at that extension that you did last year. We're looking at from that position when the force is applied, further extension. Now, because the system is originally in equilibrium before we removed the restoring force, the tension in the spring that acting will then oppose the deforming force. So the change in tension, because it's not the absolute value of tension, because there was already a tension there, but the increase in tension will be equal to the deforming force that was applied, but it will be in the opposite direction. So our equation becomes delta T, the increase in tension, or the decrease if you've compressed it, will equal the stiffness of the spring multiplied by the displacement of the mass, but it's negative in there as well. That's absolutely key. Okay, we're assuming that the displacement was linear in line with the spring here, otherwise we get a much more complex system. By Newton's second law, once we remove that deforming force, the resultant force on this system is the increase in tension we've just talked about. So by Newton's second law, we're left with delta T equals ma. That's just F equals ma applied to this particular system. And what we can do with those two equations, you see we've got two equations out there, delta T equals, we can actually equate them together. So we can have ma equals minus kx. And a quick rearrangement of that actually gives us an equation for the acceleration of the system in terms of its displacement. Okay, and what we can see is that they're actually directly proportional to each other. And that is because K, the stiffness of the spring, and M, the mass of the spring, are constants. Neither of those are going to change in the system at any point. Okay, so that's an absolutely key point to realise for a spring mass system, that acceleration is directly proportional, but in the opposite direction to the displacement. Let's have a little look at the simple pendulum, which, while it is a simple pendulum because it's just a mass on what's called a light string. If you see the term light on a paper at any point, it doesn't mean it's got low mass, it means it's got negligible mass. We can ignore it completely. So a light, quite often they use the word inextensible string as well. That means it can't be stretched out either, so the length of the string will remain constant throughout. So a light inextensible string. That will give us a simple pendulum. Now, unfortunately, the maths behind the pendulum is not quite as simple as the spring mass system. Okay, so just got ahead of myself there a little bit. So we've got the pendulum in equilibrium when the bob is hanging just below the point of suspension. When we displace it, we get the system as shown in the diagrams on the right. So the geometry of the system is shown in the top diagram, and the free body diagram of the system is shown in the bottom. So we've got tension now acting at an angle along the angle of the string, but the weight still acting straight downwards. Now the weight can be resolved into two components. Okay, it can be resolved into mg cos theta, which essentially is just balancing the tension, and mg sine theta, which you'll notice is acting in the opposite direction to the displacement. So the displacement x is to the right, mg sine theta is to the left in the same line. That component of weight is what applies the restoring force in this scenario. So you can see it's a little bit more complicated because we're not in a linear fashion like we were in the previous one. We're now looking at things at an angle. But from the free body diagram, we get that the restoring force is given by minus mg sine theta. Again, the minus sign is because we're defining right as positive, so the displacement is to the right, that was x, but our force is to the left, so it's minus g sine theta. What we're going to use some small angle approximations. So you may remember from certain points last year, and certainly if you've done maths as well, that if you have your angle in radians, then sine theta for a small angle is approximately equal to the angle in radians. So we can use small angle approximations here to make the maths quite a bit easier. Okay, so that means we can simplify that down. We can get rid of the sine function altogether, providing that we've only displaced it by a small angle. And for a simple pendulum to be in true simple harmonic motion, that's got to be the case. So we're left with the restoring force is equal to minus mg theta. Okay, in terms of the system geometry, we can say that theta is x the displacement over L the length of the string. Again, that relies actually on some small angle approximations. Don't worry if you're not following that. The derivations themselves here aren't examinable. They're just there to help you with the understanding of where these things come from. Okay, so what we can do is substitute in for that value of theta into our earlier equation. So we're left with a restoring force, which is minus g x over L, where x over L has been substituted in for theta. So we've actually managed to get rid of the angular term altogether, which is pretty handy. Okay, again, as we did with the spring mass system, we can then say, right, well, our restoring force would also be the resultant force, which of course acceleration, so equals ma. We can equate those two equations together because they're both the restoring force. And you can see, well, the m's cancel straight away, and we're left with acceleration is minus g over L multiplied by x. And again, we are left with a very similar looking format for the equation, just with different constants. The gravitational field strength and the length of the string are the constants here, but we're still left with the idea that the acceleration is directly proportional, but in the opposite direction to the displacement. And it's that key similarity that actually defines an object in simple harmonic motion. So the definition for simple harmonic motion is really simply, there it is, the system is defined as being in simple harmonic motion when it is oscillating such that the acceleration of the system is directly proportional to and in the opposite direction to the displacement of the system from its equilibrium position, i.e. acceleration directly proportional to minus x. Okay, and that's it. That's absolutely key. So all the maths we've just done there was leading to that point to make you realise that both the systems have the same outcome, the same conclusion from this. Okay, that the acceleration directly proportional but in the opposite direction to the displacement of the system. That's what defines an object being in simple harmonic motion. The fact that the two systems had different constants is something that then works when you've got to consider what kind of systems you're looking at, but even that there's a little workaround that we'll meet in the next lesson. So that's an introduction to simple harmonic motion. Okay, talked a lot, there's a lot of detail in there, but the absolute key thing is learn what's on this particular slide now. It comes up over and over again in exams. It's an easy 2 marks to get. Make sure that you've got that the two are directly proportional to each other. That's 1 mark, and they're in the opposite direction, 2nd mark. That's the key. Take that away if nothing else. Okay, see you in the next session.